Hello everyone, it's May 23rd, Sunday. I watched the Formula One game this morning. It was the Monaco Grand Prix. Quite uneventful. Quite uneventful. I think Mercedes, they screwed up their team strategy, and Red Bull executed their team strategy perfectly. So the result is self-explanatory. Alright, let's take a look what we have today. Sunday, I expect to be a hard question as well, so better get ready for that. Alright, let's take a look. Find the shortest superstring. I generally don't like strings. Given an array of string of words, return the smallest string that contains each string in words as a substring. If there are multiple valid strings, return any of them. You may assume that no string in words is a substring of another string in words. Okay. Let's see. Alex loves LeetCode. Alex loves LeetCode. Okay. Our permutation of Alex loves LeetCode would also be accepted. That is true, but we can get to the shortest of them. Okay, I see. And it's going to be a substring, so it's not a subsequence, which means the order is important, and then we cannot subtract any one of them. I mean, which means the worst case scenario, just concatenate everything. Okay. Oh, ATCG. Man, I remember that used to be my work when I was a biology student. I work with DNA a lot. So basically, we find this string is a superstring of everything. We can find everything here inside here. I'm just checking just to see CTA, GT. GCTA, TTCA, and ATGCATC. Okay, and they say none of the string is a substring of the other, which means we cannot combine any string within themselves. All right, we have 12 words, the maximum, and each one is 20 in length. So it's not a big test case. It won't be big, only lowercase. All the strings of words are unique. Okay, interesting question. So far, no clue. I don't know. Alex loves LeetCode is not going to be helpful because this is a case where there's no overlap, right? Basically means the strings have no overlap. Basically, we just try to find the overlaps, right? Find the overlaps. If a string, right, if a string has no overlap with anybody else, then that string has to be by itself, right? So which means we can start by looking for overlaps. So let's say CATG, what do you overlap with any other strings? How to find overlap? Overlap because they say that a string cannot be contained within any other string, right? It says no string is a substring of another string. That means if overlap happens, it must happen to the end of one string and the beginning of the other string. Because if you move too much, then it being containing. So basically, we're checking the end, say TG. We'll try to see if anyone has TG. Nobody has TG. And then anyone, as I get the front is a TG. Front is a G, right? Oh, we find front is a G. This one front has a G. And also anyone will end with a C. Oh, this one ended with a C. So do I say that the best scenario for CATG will be for CATG to be concatenated by GCTA, so GCTA, and on the front will be ATG CAT, like that. Now, after we consider the first one, we consider the second one. And again, N is a T, so we want something starting with a T. So this is starting with a T. So we know these two can be together. And N with a C. And this one start with a C. I don't feel like this way of thinking is correct, though. ATC. Hold on. Where does this one go? CATG is here, right? So we concatenate with GCG, CATG, and oh, ATG and ATG and ATG. I was looking the wrong way. No, not the end with the front. No. It's the end something with the front something. I was wrong. So it will be like the maximum overlap, right? It has to be the maximum overlap between all of them. All right, so that means, we need to look at it a little bit differently. When given a word, right? If we want to overlap, so with the front, so CAT, right? The maximum can match is CAT. So we need to find the end 3 characters, see if they match CAT or CA or A, right? We have an A, but there's no CA. Like we look for CA. No, oh, there's one CA. We'll look for CAT first, right? So CAT, no CAT. CAT, no CAT. So we'll look for CA. Or boom, we find a CA. So which means we have CA, and then so that is the maximum match, which means we have TT, CA, and CA can match to TG. Okay, so these two are combined, and once we combine, we can use the combined version, right? Oh, but then there could be like different ways to combine, and we want to find the shortest superstring. Or we can think about like a different way. No, so we don't know where to put this one. If we only have one, so TTCA does concatenate with that. Because I only have one. Yeah, if we only have one, that's the only way to concatenate, to make it. Because we want to concatenate the best, right? So if we can find an ending, it's not an ending, it's actually a start. If we can concatenate 2 strings, the maximum we can, and that is the best strategy. Because if we don't concatenate this way, and we concatenate the other way, it cannot be better. Can it be better if we concatenate the other way? Because eventually, CATG, this has to be concatenated with something, right? It has to be concatenated with something. And this one we can save 2 characters. If we concatenate with something else, like everything else be in the same, let's just say we have finished concatenating the rest, and we want to concatenate CATG into the rest. Now, if we want to concatenate CATG into the rest, the only way to do so is to find something that can either concatenate to the tail or something that can concatenate to the head. And of course, we want to find the most that we can do so. Yeah, I think that is the case. We want to find the most that we can do so. So which means from like this, we just want to concatenate the most. And so we concatenate these two, and we form TTCATG, right? So that's the result of concatenating these two. Afterwards, we're going to look for TTCATG and try to see what we can concatenate there. So we have the end is TTCATG, so it's the same thing, and the start is a TTCA, right? So I'm going to find anything I can concatenate with the tail of this. I mean, we have ATG to concatenate with this, so that's why we concatenate these two, right? And then we have ATC at the end. We want something And we also have the start is TT. So basically we say T we can concatenate with this, and CTA can concatenate with this. That's why we came up with this. I don't feel like this is a systematic way though. The dynamic programming? How would you do that? Well, each word will have to be concatenated with one of the other words, right? Each word has to be concatenated with one of the other words. Because eventually it's either going to be concatenated with this, or with this, or with this, or with this, right? So we can say, what's the minimum length of this concatenated with everything else? And then every time we get a new word, hold on. So we have the first. So think about this way. Like if we have this portion already concatenated, and then we want to concatenate this, that's actually not the shortest version of this. Does it produce the shortest version on this as well? I don't think so. The shortest version of this because this one, if you see that, it's at the end. I mean, that's this one, yeah, I got lucky at the end, so which means the shortest version of this, we want to concatenate, but because this thing can be, if we find a string here, right? If we find a string in front, and then we got a new string, it can either go to the end, or it can go to the front, or it can go somewhere in the middle, right? That's different ways it can go. Which means what we need to find is which way will generate the shorter string. Now, like we believe that the shorter string in the front will lead to a shorter string. It's like this might work. So the shorter string, so basically the front we can concatenate into. All right, let's try. So which means we have CATG, right? We have CATG, and we want to concatenate CTAAGT to it. So CTAATG, we can do two things. We either append at the end. Well, there's nothing, so we append at the end. Just going to be add them together. We can append to the front, which also is adding them together, or we can, but then that actually make a difference, right? We append at the front, append at the end, it changes the order, right? It changes the order and might affect the following, or we append like in the middle, but we cannot append in the middle. And the word, can we append in the middle? Well, append in the middle, we're destroying these things. So no, we cannot, because since it's a CATT, GT is here, right? It's here, so we cannot. Or just build a ground up. Or like we see which one we can concatenate with. But if we do that, what if I cannot concatenate with anybody? Maybe we should think about this backwards, right? Think about backwards. How would you think about backwards? Say we have a string that contains But the thing is, I don't know which one will be the neighbor of this. I can say it can be this as a neighbor, and then So everyone will have two choices, right? This we can concatenate with this, or this can go to front, and then we keep going. And then this can try this, and try this, and then we keep going. And that will lead to a tremendous amount of runtime, because each one I can go 4 times, and then I can yeah, that's like a brute force, right? That's like a brute force solution. We just try to concatenate every possibility. But maybe there is a way to save. Right? Let's say we have 0, 1, 2, 3, 4, right? We have 0, 1 concatenated, and then we face 3, 2, 4, 3. Or we have 0, 2. That is a sub-problem. Like after we concatenate 2, I would combine 2, that become a new word, and the problem become a 4-letter problem, right? A 4-letter problem. A 4-letter problem with different start and end. And then 2, 3, 4. Oh no, I think 1, 2, 4. 1, 3, 4. If 0 is 3, it's going to be 1, 2, 4. If it's 0, 4, it becomes 1, 2, 3, and then we can keep going, and then this one has a reverse version, 1, 0, 2, 0, right? And then we keep going. That does not feel like it's gonna grow exponentially. Like every time we have 2 versions. And then every time we concatenate, it has 2 versions. Yeah, we're trying to find like it's become permutation. Yeah, this has become a permutation. Right? A permutation is going to be 20. Right? It's going to be 12. Length is 12. 12 factorial. Yeah, that's a permutation. That's not going to work. No. There gotta be a better way. No, that's not going to work. We have to be picky on which one we can do. It's like if we have something that does match, that has a matching, then a matching would definitely be better than no matching. How do we find matching faster? Like for CATG, right? For CATG, we know it has to match to this one because it has the best match. It's ATG and ATG match. But in this case, nothing matches, right? Nothing matches. So nothing matches. If something doesn't match, which means this one doesn't contribute, so we don't consider it. Okay, that's a thought. So we keep looking, and for this one, see if anything matches. Okay, so each round, we see if anything matches. If it matches something, we record it, see like which one this one match, to the front and to the end. So eventually we'll get pairs of matching. And if I match to, if this one match to this one match to this as well, which means what we can produce is a match. And once this match is done, so yeah, we go through, then we find all the matches, right? All the matches. And then we say we want the biggest match, right? We want the biggest match. So let's say we go through this thing using this new idea. What is the match? So CATG, right? So what we have, we can use their index, right? Their index, and then no, we can actually match them. It's fine, like match. We count how many match. So CATG with this CTAGT, there's 0 match, right? 0 match. So we can 0 match on both sides. Like if it's no match, then we don't consider it, because eventually, if there's no match, we just have to keep adding on. Okay, so there's no match. With this, we have a match. So what we have is, oh god, we have is CATG, CTA. That's one match, right? We cannot match on the other side. And then this one and this one, no match. Oh, there's a match on. So it's two match. It's going to become TTCA, TG, right? That's two match. And then we go to the end. To the end, it's actually a match on both sides. But if a match on both sides, we take the one that has the better match. This one has three, which is CATG, CATC, right? That's the match. Reverse match only match C itself. So that's the first round. We find out all the matches that CATG has. Now we go to CTA. We go to the second one. Now we try to match this. Tail doesn't match because it's T as a G. Front doesn't match, so we don't consider. Match these two. Tail has a match, so we have a one match, which is CTAAGT right? And we also don't have a front match because it's an A and it's a C. Now we try to this one. GT, that's AT, no matching. CT, that's a, means CTA, CT. We match a C, right? We match a C, so there's also a one match. It's going to be ATG, CATC, TAAGT, right? That's this one. Now looking at GCTA and TTCA. GCTA and TTCA, and the ending is CTA. CTA, no matching. The front will be CA, right? CA. Oh, hold on. I got it wrong. I have to redo it. We have a match. CTA, GTA, and CTA. Yeah, it's hard to see. It's like I say C and A. No, but CTA. CTA is matching CTA. Right? CTA is matching CTA. So I'm actually wrong. So how do I correct it? Let's do it again. I think the first match we're doing correct. So here we say CTA is matching CTA, right? So it's a three-letter match with GCTA, AGT, right? And then the tail, right? If I want to match the tail, I'll pick a smaller one. So we're going to say GCT. Do we have GCT? No. Do we have GC? No. Have G? No. So that's it. Again, here, match to the front. So we say TCA, right? Do we have TCA? No. How about CA? No. How about A? No. A match to the end, we want TTC. Do we have TTC? No. TT, no. T. So we have a one match. So that one is correct. One match with CTAAGT, TCA. That is correct. And here, so we want a front match. We have CTAAG, CTAAG, no. CTAA, no. And I actually realize this can actually be a, we can cache this, like how we match. How we match can be cached. Anyway, so CTA, no match, CT, no match, and C, no match. And tail, let's see, tail, TAGT, no, AAGT, no, AGT, no, GT, T, no match. So this one has no match, right? Now we're gonna go for this one. So we have the ending is CTA, so we want CTA, CTA, no. How about TA? No. How about, no, there's no match. Front, GCT, so GCT, no. GC, no, and G, nope. So that's not gonna work. So I have to match this one. Again, CTA, we'll try to match CTA, no match. TA no match. A we have match, so this does have one match, which is GCT A TG CATC. How about the other way around? We have GCT here, so GCT no match. How about GC no match? How about G no match? So that's that. These two. Again, we'll go try TCA front, TCA no, CA no, A. We have a match, so it's going to be a one match with TTCA, TGCATC, and the front will be TTC. So TTC no match, and then TT no match and T no match. So these are all the matches, right? All the matches we have. We've listed out only 1, 2, 3, 4, 5, 6, 7. I mean 7 matches in total. Okay, now we find the 7 matches pairwise. These are pairwise matches. So we say we want to start with the one that has the largest. We have 2 largest. I guess we can take any one of these 2. I guess it doesn't matter which one we use. Okay, so we take any one. Let's just say we take the CATG CATC. So this one, CATG with CATG with this. So we match these two. So we pop this one out. This could be done using a priority queue. All right, so we pop this one out. So now what we're going to do is to match CATG CATC with the remaining values. So we have to also record who the remaining values are. Actually, we don't. Do we have to? Because we already, when we put them together, we already compared, right? We already compared. Yeah, we already compared. So when we put these two together, right, the front doesn't change, and the tail also doesn't change. Right, and then we already compare the rest, so we know which is the next one to go. So when we put these two together, right, we immediately know that the next one that's going to pop out is a GCTA with, actually, yeah, GCTA with what? With AA with this. These two are the next one that needs to be, but we choose these two, so we need to find out who I can pair, who this can pair. So this is the head. So I want to know what is the best I can pair on the head, and what is the best I can pair on the tail. So the best I can pair on the head is going to be, so I have a best to pair on a head is going to be this one, right? And the best I can pair on the tail, CATC, will be, actually no one I can pair with this, right? Like CATC, nobody I can pair CATC at the tail. Therefore, we say, okay, next one we're going to pair is going to pair it on the head, which we're going to bring TTCA in. So we bring TTCA in. Now the tail is here, the head is TTCA. Now we're going to find who TTCA can pair on the head. The TTCA can pair on the head. Actually, we find is going to be this one. Can pair. I think that's the only one that can pair. And again, CATC has nobody to pair, so we're going to pair this C T A A G T. That's going to be pair. So remainder is GCTA, and we say who this can pair to the front and happen to be GCTA. So GCTA is here. So we arrive at this solution, CAT. Okay, we did arrive at it, but I think what we need to do is we need to find out who can pair with whom on the front and on the tail. Because once we combine two strings into a new string, the front and tail doesn't change. Which means the pairing situation doesn't change. If we go through the pairing already, then we have the information. Right now we have it, so we need to have a comprehensive information on the pairing, which we can do. So each one can be paired on both sides, right? Can be paired on both sides. How do we lay this out? So we have 0, 1, 2, 3, 4. Say 0 can be paired on both sides. I want to know which one it can be paired the best on either side. So if it's 0, I say on left and on right, right? So on 0 on the right, the best pairing is going to be 4. On the left, the best pairing is going to be 0, 1, 0, 1, 2, 3. It's going to be 3. Let's only do one pairing. And then 1, the best pairing for 1, CTA, GT on the right side is going to be 0, 1, 2, 3. It's going to be 3. And on the left side, the best they can be paired with is going to be 4. Right? CTA, GT. Because CTA, GT on the right side, we can be paired. I need something like GT, right? GT or T, and be paired with this. On the left side, I need something ending with C. It's going to be this ending with C. And GCTA can be paired on the right side with, oh, I was wrong. This can be paired on the left side with CTA. I constantly make this mistake. 2 on the left side can be paired with 0, 1, 2. 2 is the best to be paired on the left side. And on the right side, the best can be paired is going to be this. 1, 2, 3, yeah. Now go to here. 2 I already paired, so we know 2 have been paired on the left side by 1, so which means 2 can be best paired on the right side by 1. How about 2 to be paired on the left side? No, wait. Yes, to be paired on the left side. So something ending with GCT. Well, nobody ending with GCT. I mean, we just keep looking. Anybody ending with GCT? Nothing. So nothing for that. Just so on the left side, just gonna be empty, and no pairing. Now TTCA 0, 1, 2, 3. We know it can be paired the best on the left side by 1. So we put 1 here. Well, actually, we have to see pair on the left. Anybody can pair on the left. This cannot be paired on the left here, so it's going to be 1. How about paired on the right? If I want to be paired on the right, it can be paired on the right by 4. And then we go to 4. 4 paired on the left will be 0. 4 paired on the, we can compare for the pair on the left, right? On the left, this one will be A on the left, and this one going to be paired ATG on the left. So the best is going to be ATG, and on the right side, this one can be paired with, well, I mean, we just have to go through the list to see if anybody can be paired on the right side as nothing. So it's nothing, right? So now we see that some of them cannot be paired with anybody. And also, like, we want to see the biggest pair. So we know 0 to 4 is a big pair, and it costs us 3. 0 to 3 is going to be a cost of 2, not a saving of 2. 1 to 3 is going to be a 1. 2 to 1 is going to be a 3. 2 to 1 is also a 3, right? And 2 to 1 is going to be 3. 1 to 3 is a 1. 3 to 4, 3, 0, 1 to 3. 3 to 4 is going to be a 1. And 0 to 4 is going to be a 3. So we say we want to take out the maximum matching. So 0 to 4, let's just say we want to take 0, 4. It's a maximum. Then we want to find the best match on the left side for 0 and the best match on the right side for 4. On the right side for 4, we have nothing. On the left side for 0, we have only 1. That's a 3. So we put a 3 here. Now we're going to find the left match for 3 and the right match for 4. Again, right match for 4 is nothing. Left match for 3, we have 1. And now we want to find the left match for 1. It's going to be 2. So and is 2, 1, 3, 0, 4. That's 2, 1, 3, 0, 4 right there. Okay, that seems to be working. I'm not sure. The savings, right? We also have to keep tracking of the savings as we go through. So we need this new data structure that will allow us to go through this process. How do we do this? So we can just use the same, right? We also want to know, not only do we want to know the best pair, but we only have words.length is 12, right? Words.length is 12. We probably can just find the maximum directly. Like we have the cost, the savings, right? And then we have a tuple to tell us which one is the front, which one's the back. Savings, and then 3 and 0. But then the question is we need to ask is, nice. Hold up. Isn't this like a graph? Of 0, we can go to 4 with a weight of 3. 0, we can go to 3 with a weight of 2. 4 can go to 3 with a weight of 1. And 1 can go to 3. It's a directed graph. So it's a directed graph. 0 has to go 4. And so we go front to back. So 3 go to 0, right? 3 go to 0, 0 go to 4. And 2 go to 1, 1 go to 3. So 1 go to 3 with a saving of 1. And 2 go to 1 with a 2 go to 1 with a saving of 3. And 1 go to 3, I talk about it. 3 go to 4 with a saving of 1. 0 go to 4. So that's the graph. We have a graph, right? So the idea is we need to find a path in the graph with the least amount of cost. Isn't that Dijkstra? Right? Is that Dijkstra? We can solve it using Dijkstra. And we have a starting point. Well, how do you know which point is the starting point? Well, any point, any node that doesn't have an in node, an in path, and that's going to be a starting point. And any node that doesn't have an out path, that's going to be the end node. And in a case that does not have, so we find all these, right? And then the letters the words that doesn't belong to the graph, they can just be added on later on. Doesn't really care. So all we care about is the words that can form the graph. So when they can form the graph, then we try to find. So we're going to start with 2. We say we go to 1, 1 and go to 3. 3 we have 2 options. We can go to 0, go to 4. So we go to 0 and 0 go to 4. But if we go to 4, then we cannot include 0. So we also have to include every single one of them. So it's going to be a graph that we have to, we have to traverse through every node. So I don't think it's Dijkstra. Dijkstra is to find the shortest path, right? Shortest path, you don't have to go through everyone. But now we have to go through everyone in the graph. So we're going to find a path that can go through everyone in the graph, but also with the shortest. Which means we can just do a DFS, right? We do a DFS and return the path that is the shortest, return the path that with the smallest cost, and actually not the smallest cost, the maximum cost. I was wrong. It's going to be the maximum because it's not cost, it's benefit. Right? We want to accumulate the most benefit. So it's the maximum benefit. As we go through the graph, we find the maximum benefit that also goes through every node. So like if we have multiple paths can lead to all the nodes, then we need to find the one that has the maximum weights on it. Because we need to get through every single node, so this is going to be a DFS. So we can just run a DFS, and if any of them do not lead to having all the nodes, we just discard it. Okay. Seem to be a possible solution. Let's try it. Let's try it. I mean, yeah, let's try it. We can make that into a. How do we handle the what type of data structure are we going to use to represent the graph? Dictionary? No. It's going to be. Isn't like the adjacency matrix? No, adjacency list. Adjacency list. So a node will go to all these nodes, and each one of them will have a weight associated with them. Let's give it a shot. So, okay, let's take a look. I think this is a hard question. All right, let's try this. I'm excited. If this turns out to be correct, I will be very proud of myself. All right, so first things first, we want to create a graph, right? So we want to create a graph, which means we want to write it in a different function. Now let's make it like this. So we want to def gen graph, right? Which means we're passing the words. It's going to be a list of str, and when I return, it's going to be a dictionary, right? Be a diction. Actually, it's going to be a list. Okay, let's see. Which one will be better? Yeah, it's a doesn't matter. It's gonna be a list. Let's do a list. So it's gonna be a list of tuple. Right? List of tuple, and the tuple is going to be int and int. It's currently my design. Okay, so how do we do this? So basically, when I say graph, it's going to be this, right? And for I word, for IW and enumerate words. Every time we go new one, graph.append, new thing. And then we're going to say for J in range, we're going to say n equals len words. For j in range, I plus 1 to n, right? What do we want is for each word, oh, that is not the right data structure. I would rather to use a dictionary because Dictionary is better. List of tuple. Yeah, that's fine. So we have a graph. So it's actually not. It's going to be a dictionary. Actually, we can say it's going to be a default dict. Let's call it default dict. So graph is going to be a default dict, and it can be a list, right? So we don't have to worry about this. So for each one, we need to do a compare on the front and on the back concatenation. I want to find how much similarity the two has. Is there an easier way to do this? We can go like 1 because it's 2. How can we do this? I might have a way, but so anyway, we're gonna write another function, right? We're gonna have to write another function called def concat, right? If we want to concat w1, w2, both are going to be str, and what we want to find is what we want to return. What do we want to return? We want to return the tuple. Now, we want to return an int. How much savings we can get by concatenating these two. So yeah, so let's say W1 and W2, we're always gonna try to concatenate W1 at the front, W2 to the tail of W1, okay? So what I want to do is, we're gonna say, for I, while I equals, so we're gonna say mn equals len W1, len W2, right? So we can say for I, I'm gonna go through the entire thing. Yeah, for I in range, the small of m and n, right? The small of these, and -3, small of these two, yeah, and small of these two -1, because we know that they're not, so we can do -1 or 1 less, right? I'm going to start from here all the way to 0, -1, right? What we're going to do is W1, we're going to take I, right? So this is going to be -I, something, no, -I to the end, right? -I to the end, so we're going to start, say like a 3, so -3 to the end, and equals W2, that's going to be the front, all the way to I. Alright? Okay, I, if I is 3, going to be -1, -3, and it's going to be 3, 0, 1, 2. Yeah, so we do this. We say if they're equal, and return I, right? So that's the amount that we can save, the maximum amount we can save. If nothing happens, like doesn't equal until it's going to be 1, and if 1 doesn't equal, then we're going to return 0. That means we cannot save anything. So actually, I'm not sure if this is correct. I think it is. So we take the smaller of the two, the length, and then we length -1, and that's the length, right? That's the length we want to compare. So in the front, we go minus the length, then we get us to that, and the back we're going to do 2I, that also get us to that, and then we want to find the first one that does match. If it match, return. If it doesn't match, that means it's nothing. I think it's good. I think it's good. So let's concat. So here we have two words. One is W, and the other is going to be actually it'd be easier to range in, right? Range in, easy. So we have two words, word 1 and word 2. So we can say saving 1 equals self.concat. Yeah, concat. Let's call it concat save. Concat save. We're gonna say I want words 1, words I, and words J. We want to pair words 1 and words J. Words 1, I is the front, J is the back. And now we have another one. It's going to be words J is the front, I is the back. So if what if they're the same? What if they're the same? So if a word I can pair at the front, I can pair at the back with the same amount. Yeah, I can see. If it's the same, that just means the path is bidirectional, right? It just means the path is bidirectional. So if 1 and 2, we can go 1 to 2, and we can go 2 to 1, right? I don't think it affects. Yeah, I don't think it affects. So we'll just say when we record the one that's if S1 is larger than S2, right? S1 larger than S2, then we take S1, which means we're gonna say graph graph I, right? Dot append a tuple. What is the tuple going to be? So we say the first one is going to be the cost, the savings. Now let's say the first one is the actual one we're going to go to, and the second one is going to be the savings, right? So I can go to J, right? And say elif. Yeah, if I can go to J, then J cannot go to I. Elif S1 smaller than S2, then we say graph J dot append I, so J can go to I with savings 2. Else, elif S1 is not equal to 0, then graph I dot append JS1 and graph J dot append is IS2. Maybe we can save this line. I don't know, can we save this line? Yeah, I think we can. We can just say if this is larger than equal to, right? And then we say if this is smaller equal to, right? And then if this larger equal to and S1 is not equal to 0. I think which is for the if S1 is equal to 0 and S2 is equal to 0, then we just continue. Elsewise, one of them is not 0, so we just say if and if, right? That's it. So we loop through, then we create a graph, then we say return graph. Okay, let's stop here and just run this. Just run this. So graph equals to self dot gen graph words and just print graph. I just want to see how it look like and do it step by step. Let's see if this one works. And we're gonna just use one of the test case, and the only test case. Use this one. All right, and then we can put this in, but it doesn't really matter. We're not gonna generate any answer yet, so we're not ready yet. We ain't ready yet. We're still in the process. Okay, so again, we can do all of this. Be this, and the comma can be like this. So here, this is going to be words, and this is going to be shortest words. Run it. Ticked is not defined. Probably we need to do not directly print it, but I'm going to say for key value in graph.items, print key value. Okay, so here's what we got. 0 can go to 2 with a 1 and 4 with a 3. 0 can go to 2. 0, 1, 2. Oh, 0 can go to 2. And 3 can go to what? 2 with a 0. That's not, no, 3 go to 0. I bet. 3 go to 0 with a 2. And 3 go to 4 with a 1. Yeah. And 2 can go to 1 with a 3. And 2 can go to 4. 2 can go to 4. 0, 1, 2. 2 can go to 4 with a 1. Oh, yeah, that's true. 1 can go to 3 with a 1. And 4 can go to 1. 4 can go to 1 with a 1. Okay, so let's draw it out, right? Let's draw it out. Let's see. I'll find a sketch pad. Yeah. All right, this is what I did last time. Can I delete this? How do I delete this? New. Blank. Yeah, so we have 0, right? We can go to 2 with a saving of 1. And 0, we can go to 4 with a saving of 4. With a saving of 3. And then 3 can go to 2, so we'll have another one here. Okay, 3 can go to 2. No, 3 doesn't go to 2. 3 go to 0. So 3 go to 0 with a saving of 2. And then 3 go to 4 with a saving of 1. And the 2 go to 1. No 1, so 2 go to 1 with a saving of 3. And 2 go to 4 with a saving, 2 go to 4 with a saving of 1. And 1 can go to 3 with a saving of 1. And 4 can go to 1 with a saving of 1. Right? So the job now is to find who is the starting point. Actually, with this graph, we don't even know who the starting point is. But I guess it doesn't matter who the start. Well, if we have a node that doesn't have an incoming, well, every node 0, 1, 2, 3, 4, so everybody can come out. So nobody seems to be the endpoint, and everybody can come out. So yeah, it's actually interesting. Like, how do we determine which node to start with? Do we start like with 0? Okay, we start with 0. We can go 0 to 4, 4 to 1, 1 to 3, and we got stuck. So we cannot go with 0. because it will go 0. Oh no, we can also go 0 to 2. So 0 to 4, 4 only go 1, 1 only go 3, and 3 return here, go here, not allowed, but we don't hit 2, so that's no good. We're coming back, nowhere else to go. Coming back 4, nowhere else to go, so go to 0 again, so 0 comes to 2. 2, we have two choices. 0 we have two choices as well. We say we go to this one. So 2 have two choices. Doesn't matter, we pick any one. So we say 0 to 2, 2 to 1, 1 to 4, no, 1 to 3, 3 to 4. Now that's a path, 0, 2, 1, 3, 4. And we accumulate, say 1 plus 3 is 4, 5, 6. We have 6 savings. Coming back, 3, we go to 0, and we don't go to 0 because we went there already. Go to 1, 1 has nowhere else to go. So coming back to 2, and then we can go to 4. So 0 to 4, 4 can only go to 1, and 1 go to 3. So 0, 2, 4, 1, 3. 0, 2 is 1 plus 3, that's 3, plus 1, 4. 1 is 3, 4, and that's 5. Right? That's 5. So we only have 5 savings. So earlier 6 savings is better. So that's go from 0. We're done. Now we're gonna go from 2. Go from 2. We do have to go from every single one of them, because we don't know where is the starting point. We'll go from 2, we're going to go this, right? So 2 to 1, 1 to 3, 3 to 4, and that's it. We can now go anymore. And also 2 to 1, 1 to 3, 3 to 0, 0 to 4. That is 3, that's 4, 6, that's a 9. So that's the maximum we find. But we don't know, so we have to keep going. 2 to 4, 4 to 1, and then 1 to 3, 3 to 0. Yeah, that's another one. 2, 4, 1, 3, 0. We can do that as well. It is to find the path with the longest. Maybe we can but if each one is a different starting point. Like we don't know, right? Always say we want to always go through the one with the largest. So we want a 2 to 1, or we want a 0 to 4. So we go 0 to 4, and then we find 0 to 4 is not working, so we go 2 to 1. But we don't know that it's a starting point. So we have to go through every single one. That seems to be very costly. 2 to 1, 2 to 4. Yeah, how to find a path that connects every node in a graph, that also generate the largest weights. That's a good question. I don't know. There might be an algorithm for this. And you don't know the answer, right? At this point, you don't know the answer. Yeah, we don't know the answer. We have to go pick every single one as a starting point and go through them. That just seems to be very, very very stupid. Like if we know which one is going to be the starting point, that's going to be easier. Like if there is any one that nobody goes to, how do we know if there's anyone nobody goes to? Like if we have one that's not here, right? That's missing in the key. That means there's someone don't go anywhere, and that's the end. That's the end. We want to know who can be the start, which means is whom that nobody goes to. It'll be hard, right? So maybe we do go through every single one. We do go through every single one, but we can, it's hard to cache because at every start, like we get every node, we have a past state, like who has been visited already. And this past state is like if we encounter the same state, then you can say how much. And there could be some level of cache, like at the current node, right? At the current node, if I know what has been visited before, then my result will be exactly the same. Okay? So what we can do is we can use a list as the, this is not going to be a key, but what we can do is we have numbers, right? The nodes that have been visited before, and then we can sort them, turn them into a string, right? Sort them, turn them into a string. That's deterministic, and then turn them into a string. That does not sound deterministic. I mean, like we can, but it involves some process. We'll turn them into a string because I need a key, right? We turn them into a string, and we say if we have this is a state and a string, that together could be a key. It can be a tuple, so that's a key. So we can say if this one has result already, either it's a success or it's we can say if it's a fail, it's going to be negative infinity. If it's a success, then we can report. We can report what is the current sequence. Otherwise, oh man, let's not think about cache for now. Let's just try to solve it. So yeah, basically what I think is we have to go through every single one as the starting node, right? So I think we need to have another one, another function. Let's call it DFS, right? So I'm gonna call it DFS, and we're gonna have a node, right? We're gonna have a node, and we're gonna have the node that has visited, and the visit node. I'm gonna make it a list because the most is 20. No, my most is 12, so I can just call it. It's fine. The node is actually going to be an integer, right? And what we're going to do is we're going to accumulate. So current savings, right? We're going to accumulate the savings, and at the end, we're going to say it's going to be a result. Result is going to be a thing. The savings is going to be negative savings, and it's going to be a list of visited, right? So that's that. And this one's going to be return none. So what we're going to do is for each node at the start, for having a node, we're going to say for the next node in graph node, right? Next node in graph. So I'm visiting my current node, and then I want to go to the next node, right? Next graph in the next node, and it's not going to be next node. It's going to be next node and savings, right? So the next node and savings. So I want to go to the next node. What I'm going to do is well, first of all, the node, I'm going to say visited.append node, right? I visit my current node. So I put my node into it. Now I'm going to check for the next node. And I'm going to say if no, let's check it here. Say if node in visited. Then I'm going to check if len visited equals, so I have to have n as well. Right? I'm going to say if len visited equals n, that means we visit everybody. Then we're going to compare current savings with the result. I'm going to say if current save is larger than result 0, then result 1 equals visited, copy it, right? Well, actually, we can make that into the string directly. Oh, wait. When we make the string, it's still going to be troublesome. So we have to get the string out. Oh man, we have to like do one more time. We already did it. Ay, ay, ay. We worry about this later. So if the current saving is larger than the saving we have, then we update it, right? Otherwise, we don't consider. If it's not equal to n, then we also don't consider. We just, like that. Else, if node is, basically it's going to be if node in this and and then we have this. Actually, no. No, if node in visited, right? I'm going to say if this and this, we're going to do this and return. Yeah, because that's the end. That's the end. Now, otherwise, we're going to append the node, right? Where this is the current one I visited, and then the next node and the save. And we'll just say, we don't do it here, right? For next node, we just call it DFS. Next node, visited, right? We visited the current node, so next node we haven't visited yet, but we're going to check if it has visited. And then current save plus save, right? Let's go to the next node. And when it's all done, next node, we all visited and visited.pop, right? Because I visited my current node and I try to go to the next node, and when the next all visited coming back to me, I pop myself, I return to the previous one, right? So I'm gonna go pop. So that's the DFS. So we're gonna call it for node in range n. We're gonna say what we're gonna say. Actually, no. That's not gonna be n. That's gonna be len graph, right? It's gonna be a graph. That's because it's some word might not be in the graph. So it's going to be this node in range. Actually, no, not in range n. Node in graph.keys, right? And then we call DFS node. Visited is going to be an empty, right? And then current saving when we start is going to be 0. I have no savings at the beginning. And then we go through, see if it's equal, node not in visited, right? So we're going to visit to put the node, go to the next node. If there's no next node, right, we're going to just pop, and then that's it, right? That's it. So this one doesn't change anything. And then we'll go to the next one that we have, then we go through them. Coming back, Okay, okay. So this one shall give us, let's print result after we run this. Let's see what we have. Okay, so I forgot to update. res0 need to be equal to current save. All right, so this is what we have. 2, 1, 3, 0, 4 with 1 plus 3, that's 5, 6, 7, 10. 10 savings. Yes, we got it. That's correct. Right, that's correct. Now the job is to turn this into the answer. Now we already have how much is going to save, right? We already have in the graph. We know how much is going to save, which means we're going to go through this. We also need to, all right, so we have the saving, so we have the thing, or have the thing out. So now what we're going to do is all words. So words set going to equal to a set, let me say range, len words, right? That's everything in this word set. Now what we're going to do is res. Probably not a good idea to call it res. Res str, starting with this, I'm going to say for hold on. What would be the best way to do this? We can just take these two out, concatenate it, and then take these two out, concatenate it. Yeah, we can just concatenate it, we get a result, and then focus on these two, concatenate, get a result, which means when we start with this, right? So the result, this is actually not going to be this. This is going to be words res 1 0, right? That's the first. Then I'm going to say for I in range, right? I in range. Actually, not only that, we also going to be say words set that remove res 1 0, and then we range from a 1 to len res 1. All right. Now, every time we have current coming out, right? Current coming out. So we're gonna say the number of savings. So the save equals what? Equals the graph. The graph. I don't know it. Right? We don't know. Because the graph is a list. The graph is a list. The graph cannot be a list. The graph cannot be a list. I think each single one cannot be a list. No, it has to be another dictionary. It has to be another dictionary so we can refer to later on as well. So this has to be another dictionary with int and int. So it's not going to be like this. No. It's going to be int and int, which means blah, blah, blah. Graph I is going to be a dictionary. So how do I do this? I think I can do set. No. This is not going to be a list. This is going to be a lambda, right? And it's going to be a default dict. No, it's going to be a a dictionary, right? It's gonna be a dictionary, which means that's just a dict. I think we can call it a dict. Yeah, it's gonna be a dictionary, which means graph I is gonna be a dictionary, and we're gonna call it J equals S1, right? And this is gonna be, we call it I equals S2, right? Now, when we do this, this is all fine. It's here. This is going to be dot what? That's a dictionary dot items, right? That's the next node and save, and everything else is the same. We can prove it by just print out the rest again. Yes, that's correct. But by this simple change, we are able to call it graph I minus 1 and I. That's the save, right? We have the save, which means our result str gonna be plus equal to, this is the savings, right? And it's going to be words res1 I, right? That's that word, and this amount of saving, so we just going to go this amount of splicing, and I'm going to print res.str. Let's see what we get. Hey, we have a key error. Key error 1. Okay, don't panic. Do not panic. That is correct, because this is going to be not this, but res1. Why do you do this to yourself, man? Why do you do this? Let's just spread it out. It will be easier. So it would be max save, right? Max save. Let me say minus 1, and we're gonna say res list equals this, right? And then every time we just say this could be max save, right? Max save, and we just say res list equals this, and max save equals this, right? And then for here, this is fine. This is just going to be res list. Oh, so much easier, right? Res list, and this is just going to be res list, and I'm going to say res.str plus equal to words. This is going to be res list. So all of this actually can be turned into res list, right? And the res list I, that's the current word, and res list I minus 1, that's the previous word, and then we got I, that's the savings. What the hell? Local variable defined. Oh, shoot. That's the truth. Yeah, now I know why I do it the other way. Okay, fair enough. No, we cannot do it this way, because we're not passing it. We are doing it on the outside, so we cannot. Okay, so that's fine, It's just a little bit more complicated, I minus 1. Now we have another key error. Oh, this one I don't understand. I minus 1 till I. Hold up, let's first see if this one's still correct. No, it's not an SSTR. What we want to say is res. Yes, it's still correct. So it's just the conversion part. We still need to work on the conversion part. This I think is fine. We can do SSTR. Yeah, that's fine. So still, we're gonna go through, right? This is what we're gonna go through. We're gonna go through res1 is this thing, every single one of them, and go to 1 to the end, okay? And then we're gonna find the words, right? This is the one part, which is res1I, which is the index, and we're referring to the word, okay? That's fine. And this one is a splicing. I want to know how many savings, right? The savings we're gonna get from I minus 1 is the previous word, right? So that's leading to. So this is the previous word, I minus 1, res1, I minus 1. This gives us the index of the previous word. So we take graph that's the previous word. And I want to know the current word. That's not I. That's the res1 I. And we want to take this. That's the one. That's actually not the one. Are we missing something? GCTA A. This is not correct. Hold up. Let's get a few more out to see where we got it wrong. How about word set? It should be an empty set. No, it's not an empty set. There's stuff in there we did not get out. Oh, because I didn't call it. Where's the set? Now remove res1 I. Okay, I did remove everything, but the thing is not right. Strange, very, very strange. Previous one connected to my current one, and then why is this plus equal to? Let's print the res str as we go along. So GCTA, okay, we also want to print out, let's also print out the result, right? So 2, 0, 1, 2, GCTA is the first, that's cool. And then gonna be GCTA, right? GCTA to 1 here, so CTA is GCTA AGT. GCTA, where's AGT? Where's AGT? Right? That's the problem. That's 1, 1, 0, 1. It should be 1. Words 1, 0, 1. Is this one? Hold up. 1, I minus 1. Yeah, it's 2. Graph 2. And this is going to be res1, 1, graph 2, 1. Yeah? Should be 3, right? Let's try it. Print every single one of them. Let's make sure this is the one we're looking for. And then I'm going to print graph. Right? Let's see. Yeah, first the GCTA, and it's 3. And Oh, I know. Ah, here. That's the error. It didn't print. It print out. Yep, I think this one's correct. Okay, so this is the result. Right, so we have the result, and then the rest is anything the word set, which means these are not included inside, not included in the graph. So let's say for I in word set res str plus equal to, and that's just index. So maybe words I, and when I return res str. Okay, and then we're gonna also try. I think we can try this one. This one should be correct. This one has no graph. And this one has no graph, so hopefully the result can be accurate as well. I mean, the result can be anything. All right. Okay. Ah, yeah, index out of range. Yes, it will index out of range because nobody is inside the graph. Which means what we need to do is instead of doing let's say if not res1 return dot join words. Right, so just it's nothing, right? Nothing, and then we can just do this. Actually, we don't need to make it into because only 12, right? Let's not make it more complicated than it already is. It's actually fine. It's actually fine. So we can actually do it this way, right? We don't have to. We can just say return. Yeah, we can just say return plus dot join word set. Yeah, both pass. Okay. Gigantic solution. I don't think we didn't use deck. We'll use everything else. All right, let's hope this one passes. If it doesn't, then we have to check the answer. It's been an hour and 30 minutes. All right, hoping that this one runtime error. Dictionary changed size as iterating. What? Okay, this one I can investigate. What the actual hell? Dictionary changed size. I don't have to do anything right now. I just want to investigate why the dictionary changed size. Doesn't make any sense to me. I didn't change size. For node in this keys, dictionary changed size. Where? For node graph keys. Uh-huh. How did it change size? I didn't do anything. What the hell? I didn't remove anything. A, B, C, D, E, and C, D, E, A, right? Hold up, hold up. I'm gonna comment out all these, and let's just take a look at the graph. So 0 to 1 to 3, yeah? And then I say for node, so it's 0, right? And the 0 coming in, 0 is not in, so we go here, visited append 0, so we append 0. And next node, save equals graph node, graph 0, this one, dot item, 1, 3. And then go next node at 1. Visited has 0 in it. Current save will be 3. Coming 1. 1 is not in visited. Hold up. 1 is not in visited. Because 1, I pass 1 in. 1 is not in visited, so we append 1 and trying to find. So 1 doesn't have. This is a trouble. 1 does not have. Yeah, one does not have. Let me think. I think the way to solve this is we're gonna put it not here. We're not gonna put it here. We're gonna put it here. So we say next node, right? So when we enter the current node, is already labeled as visited. So visited, then we go to the next one, and then we're gonna pop here, which means when we go through, this is not gonna be this. It's gonna be node. We already visit node, right? Coming in, and if we do this, then we're fine. Then we're fine. Okay, so slight change to handle some edge cases. What the heck? Oh yeah. Man, what are you doing, man? What are you doing? This is ridiculous. We can just not this, not join. It's gonna be words I for I in this. A, B, C, D, E, C, D, no. No. That's still inside. That's still inside. Hold up. Still not correct. Still not correct. Let's try, let's print res. Res is 0. How? How is res 0? So visited is 0. Oh, of course. You put this in already. Ay. No, 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 no. This is gonna be this. No, this is not gonna be put in here. Put in here. But then it's already in. No, that's also not right. Jesus. How? Where do I put it? A node coming in, and I want to put a node inside, right? A node coming in, so I'm going to visit it. Now let's go to the old version. Right, let's go to the old version. I'm going to say it'll be here, and then I'm going to pop here. The problem is when we go to the next node, right? The problem is when we go to the next node, coming out, the next node is not in visited, right? It's not in visited because, but I am visited, right? Which means Why would that not be visited? If node is visited, now we can check. And if check is good, equals n. N is the length of the graph. But the graph only has one. Yeah, that's the thing. The graph has one. Because it's a single graph. Oh, the number of nodes in the graph. That's not the length of graph because some node. Yeah, that's a graph issue. That's not a logic issue. That's a graph issue. How do I solve the graph issue? So the visited append, right? And then we go to the next node. And if the next node is not in it, and a visited dot append the next node, right? We append the next node. And then it does not have or we just append the next node first. But we still don't know like the length. What if we do this one on the top, right? We'll do this one at the top, and we say we check if the visited equal to the total number in the init. If it's init, we do this and then we go out. If it's not init, then we keep going, and we keep going. It could be it could be the end. So that's an idea. So every time we visit the node, we will put it in, and we don't need to check this. We just check this one directly, and we say if it is n, right? And then if it's this, return. Otherwise, we return, right? Otherwise, we try to find the next node. And if there is a next node, then good. If there is no next node, and then this we're gonna that's fine. It's gonna be nothing, right? So I think that can go, but then the n is not right because n. How do we right? That means I and j are inside. So what we can say is graph j is just going to be equal to a dictionary, right? But it's going to be an empty dictionary because it doesn't go anywhere. Okay, so I can say, just to acknowledge that j, graph j is going to be an empty dictionary. No, that's not how it works. I'll be back. Now there's another way. So as I was going through, right, all we want to know is how many nodes are in the graph. We can do it here. We can do it here. We can have a graph, right, and we can have isolated. These are the nodes that are isolated, right? So whenever this happens, we can say isolated.append I, right? I, which means I doesn't go, hold on. That just means I doesn't go to J, but we have to wait until the end. Okay, so for each one, I want to have say is ISO, right? We say that's going to be a false, right? That's going to be false. And this is still going to be a continue. We'll go to the next one. Every time it does go somewhere, but it happens that if I do not go anywhere, but other people go to me, right? Then I'm still good. No. What we're gonna do is every time that there is a connection that's made, I am going to remove myself. So isolated is going to be a set of range, len, words, right? Isolated is going to be a set of range of len, words. And then every time that there is a connection made, I will just say if I in isolated dot remove I, and if j in isolated dot remove j. Gotta be a better way, right? Gotta be a better way. Let's continue. Right, and else. Gotta be a better way. So we can do like else. If it's an else, then we can do this. So we can say else if this, right? And then we say if I, then remove I, and j remove j. So we're going to return this and isolate it, right? So we're going to say graph and isolated equals this. And then we can print out, yeah, let's don't do this. Right, let's don't do this. I don't do any of this. I don't do any of these. Just make sure that we're going to print graph and we're going to print isolated. Those are the ones that has no friend, right? Now isolated, it's good. So now we know len visited equals, because we add this already, so equals, this is the total number of nodes inside. So this is going to be not len graph, no. The total inside is going to be, I'm going to call it here, n is the number of nodes, num graph nodes equal to len words minus len isolated, right? And then that's what we compare to num graph nodes. And now we can do it. We can call this and we can print res. Now res is this, and then we can do this, right? So what we do is, if not, we're going to just join it. Otherwise, we don't have to do this because we already have the isolated. So we don't have to do any of the removal. We just need to get the words that's in the path. So now these are the words that's in the path. Or we construct that, and we're just going to say for I in isolated. Yeah, and this is going to be A, B, C, D, E, A. I know we're going to try other two. Ah, we got a recursion problem. How? How do we get a recursion problem? Nothing's changed here. Which one? Which one gives us a recursion problem? The first one? Yeah. Why? I add a node. I check. I say if it's equal, right? If it's equal, we're always going to return. If it's not equal, we try to find the next node. And if we do not have a next node, then I just pop. What's the problem here? I don't know. What's the problem? Let's see. What do we get? What node? Well, we got into a 0, 2, 1, 3. Well, go back to 0. I think we have to set. Yeah, I know the problem because we're checking the length, right? We're checking the length. Equal, then it's larger. If it's larger, we just return. But I think it's easier way. Like we're gonna say if next node not in visited, right? Then we do this. But then we have to check if it's visited, which means that's fine, I think. Yeah, we can just check in visited. If it's not in visited, then we go. If it's in visited, we don't go. Okay? I'm pretty sure there might be more bugs that's facing us, but let's try it. And then use tuple. Okay, then use tuple. Okay, if I get a timeout, and that's it. I'm gonna call it a day. I'll try it. Yeah, dictionary change size again. What is the problem this time? Change size. I actually don't understand why the dictionary would change size. Oh, of course it changed size because I'm adding. Yeah, it will change size. No, Oh, hold up. Anyway, so I think I know the problem here because this is adding the node into it. Does that mean the original one will be correct? Okay, add a check. If node in graph yeah, if node in graph, then we do this. If the next node not in visited, len visited equals this. Okay, let's let's try it. Another hacky way. Let's try this, see if we can get it correct. What do we have? I think it's fine. Try it. Nope. Nope. I do this, NXV, ONX, XVF. No, this is absolutely wrong. This is absolutely wrong. How? I didn't find anything in this one. The hell? Why? Why? Why I didn't find anything? Like, there's no... Like, the graph is nothing. Right, the graph is like nothing. One step at a time. Let's try. Let's see what the graph is. Print graph. We have a graph. We have a graph. How come the traversal of the graph doesn't work? The graph is right. I mean, I'm not sure if the graph is right, but you can do. Let's try it. The graph looks right. What do we have? We have 2. We can go to 0 with cost 1. We can go to 1 with cost 2, not cost savings. And we can go to 3 with cost 1. 1 can go to 3 with cost 2. 1 can go to 4. 1 can go to 4 with cost 1. And 3 can go to 4 with cost 2. Alright, so our trajectory is it's not a complete graph. 2, 1, 3, 4. I see. Holy moly. That changes everything. That changes everything. Which means what we're trying is just find the maximum. Just find the maximum savings in the graph. Find the maximum savings in the graph. But the maximum savings, and it could be that the maximum savings. What if we yeah, I see the problem because it might not cover everything, right? But the maximum savings doesn't guarantee that that's the longest node, like the most nodes will be included. It could be one that contains gigantic savings compared to go with everybody else. Would that still be a better solution compared to, like, if I have a one path that have like only 2 nodes, right? The saving in the 2 nodes is more than the savings of going the other path, right? So eventually I choose those 2 nodes, and then everybody else. Then is there a possibility of like we can have 2 separate things, right? We have 2 separate things, And then when they combine together, it's the best. It's massively, massively complicated. Yeah, I say I have a graph. There's no guarantee that a graph is connected to each other. Right? I have a graph, and then I'm going through the graph to find the maximum savings within this graph that have to cover everybody. And this is on the premise that if I cover everybody, there will be more savings compared to I don't cover everybody. But that's just simply not true, right? If I have like 2 words, right? And then they have a massive savings. And then I go other words, they don't have savings if I go other words. Or like small savings. Like with a small savings going other words. Now in this case, 3 savings, 1 savings, and 1 savings. And I go to maximum saving, but after the maximum saving, I can still traverse the graph, and we can have the maximum saving. But the maximum saving, if the graph is not connected, like if I have 2 separate graphs, how do we do? And in a graph, what we're looking for, right? We're looking for the maximum savings. What if we have maximum savings, which is more than concatenating other things? If I have a maximum saving that's more than concatenating everybody else, all the others are going to be considered, like, are they not concatenating by themselves? They still have to, right? They still have to. So basically we just need to remove the best, right? We remove the best, and the remaining need to still be in, they still need to consider, right? We remove the best path in it, and then the remainders still need to create this. We still need to do it again, so they can give me another one until there's no more paths that can be generated anymore. And then the rest just... Do you want to push for this? We have Ghana to push for one more time. I mean, okay, let's just, the last idea. If this one doesn't work, then we're not going to push anymore. So, what I know is we don't need to do this. No such a thing as isolated. We just give a graph, and a graph is actually, we're not sure if it's connected. It can be connected, it cannot be connected. And that's now the goal. And the DFS, the goal is just to find the current best. And we are going to run the DFS actually multiple times, right? We're going to run the DFS multiple times to find as many paths as possible. So each run we're going to return the best path, and then we're going to remove those nodes, and then we're going to run again and run again, right? That means what we're going to say is, I don't know. We need to remove all the paths. I'm going to just say while graph, right? We're trying to remove and each one, what we're trying to do is we're just updating, right? We're just updating, and I say if it's larger, then I update it, and after we update it, when do we stop then? Well, we stop when we cannot go anymore. Right? We stop when we cannot go anymore. So we can just do like this. So one run will generate in the second run, and if it's nothing, the visited current savings. If I'm in the graph, I will generate some savings no matter what. Right? I will generate some savings no matter what. So while graph, I'm gonna say, yes, I'm losing my voice. So for node in graph, I go through everything, and I'm actually going to pass in one more thing. This thing. I'm pass in this thing, and I'm going to call a result here, and pass result, pass a result. So every time we go in, then we'll get a result, right? And then what? I'm trying to do is every single time the graph, we're gonna say we have result str, and when we get in, after we're done, right, after it goes through, we have path is this, right? We have the path. Then we're going to turn the path and say if I have path, then we're going to do this, right? If I have path, I'm going to go through the path, and say cart temp, right? And then this is going to be path, right? We're just going to go through the path, get my temp up. That's if path. If what if there's no path? Well, then there's no graph, right? There's no graph. And we're also going to see nodes. Going to be, we call it set range len words. Right, that's all the nodes we have. And first round, after the round comes out, we want to reduce, so I have a path, right? And we say for p in path and for node in path, oh, I want to use node. For p in path, we want to remove it. When you say if p in graph, then graph dot remove, I think it's a del graph p. And then if path, want to build a temp, but every time, actually we can do it here, fp in graph, and then we can also say nodes.remove p. So these are the ones that's considered, right? So now if path, then temp is this, we get a temp. And then we say res this plus equals to temp. If no path, then we don't do anything, right? And I'm not sure. Once we're done, which means we exhaust the graph, then we say return res str plus whatever remaining nodes, join words I for I in nodes. Have key error. 10 plus path I. Oh, I already removed it. That means we have to do it. First get the path, and then remove it. Okay, we pass. How about the others? I really cannot talk anymore. Okay, we have a fail. But it could be the fail. So let's also not print out. So what's this one? I didn't get the result for this one. So I'm not sure if it's a pass or it's a fail. Which means I have to go this one inside. Oh, that is really cool. Expected answer is this. I think I got to answer this, which I think is fine, because it's the same length. Right? They all pass. Okay, I really have no more energy. This is my last shot. If this is not correct, I am giving up. We're on 2 hours and 13 minutes. Okay, let's try it. I have no confidence actually. I know. Key error. Key error. Why would I have a key error? Why would we have a key error? I said I want to stop, but I can't. Because I just have a key error, which means it might be fixable. It might be fixable. Is nodes.remove p. How? How is this possible? How can we have a p? Let's print the path. How is 1 appears again? Because 1 is not in the graph. 1 is not the starting node. Take a look, 1 is not the starting node. That's why 1 is not the starting node. 1 is. 1 is. 1 is the starting node. But 1 is inside. 0 can still go to 1. Okay, what if I do this? And we have if node in graph, yeah, if the next node not in visited, and next node in nodes, then we visit. How about that? I don't know the answer, so we probably should try to find the answer here. I just want to know the answer. Oh, but they don't give me the answer. So I think print, one more print. So every single time we'll also check whether the node is in it. Okay, run it. Okay, they seem to be correct. All right, let's try the other. Okay, try one more time. Pending. Wrong answer. All right, that's it. That is it. And I'm actually going to stop because I really can't talk anymore. Wow, what a difficult question. I'm gonna give up. I'm gonna check the answer. I'll report back tomorrow. See you guys tomorrow. Adios.